Thanks for the invitation. Uh, this talk will be based on two joint works. One, many sparse cuts via higher eigenvalues. This is joint work with Anand Louis, Prasad Titali, and Santosh Vempala. Anand Louis is visiting for the whole semester here, and he's in the audience. And Prasad Titali is also here. And the second paper is making the long code shorter. It's a whole bunch of people. Johan is here for the whole semester. Okay. So what is the problem? So I'll start by defining a computational question. So the question is the following. It's called the small set expansion problem. So first, throughout this talk we'll be talking about regular graphs. Many of the results extend to general graphs, but we don't. So we have a deregular graph, and the expansion of a set is just the number of edges leaving the set divided by d times the cardinality of the set, or the denominator is just the number of edges incident in the set. And you pick a random vertex in S and you pick a random neighbor, what is the chance that you get out of the set? That's expansion. It's a number between 0 and 1. Right. So now the expansion profile of a graph, you're given a graph G. The expansion profile of that is defined as follows. Phi sub G of delta is the minimum over all sets of size at most delta of the expansion of the set size. So it's just measuring the expansion of sets of different sizes. And the small set expansion problem is just you're given a graph and you're given some constant, and your goal is to approximate phi sub G of delta. Okay, so it's a computational problem. Okay. And we want to approximate phi sub G of delta, which is this expansion of sets of size delta. So let's take even a very weak version of this. Let's say we just want to distinguish between the two cases. So you're given a graph, and let's even fix delta. You're given a graph, and you just want to find out if the expansion of sets of size delta is less than epsilon or more, or at least a constant. So you just want to find out if phi sub G of delta is less than epsilon or at least 1/10. So in one case, G has a very highly non-expanding small set. In the other case, G is a delta small set expander, meaning every set of size delta in the graph has expansion 1/10. So you just want to distinguish between the two cases. You can see that this corresponds to just approximating the value of phi sub G in a very weak sense. And I will use the term small set expander and delta small set expander throughout the talk. What I mean is this: sets of size delta have expansion at least some constant 1/10, and I will also think of delta as some arbitrarily small constant. Okay, so there are lots of algorithms for sparsest cut, which corresponds to phi sub G of half. So in particular, Cheeger's inequality gives an approximation algorithm, and there's a log n approximation by Leet and Rao, which was improved to square root log n. Okay. But when it comes to small set expansion, if you want to approximate expansion of small sets, there wasn't much work until recently, and recently people started looking at the question, I guess, and we have this approximation right now. So you can decide if phi sub G of delta is less than epsilon or more than this number, square root of epsilon log 1 over delta. And this still doesn't solve the problem that we had in mind, because if the set size is small, this number could be more than 1. So it still doesn't answer the question of distinguishing whether a graph is a small set expander or there is a small set whose expansion is epsilon.
So you think of it, you're fixing delta and taking smaller and smaller epsilon? Because what you said is not...
Right, sorry, it's fixing epsilon and arbitrarily small. Yeah.
Okay.
Yeah. We should think of epsilon delta as constants, but for a fixed epsilon, you pick arbitrarily small delta.
Okay.
Yeah, sure. Yeah, so that's the state of the art. And we also sort of know that if you could improve the dependence, even the dependence on delta here by a little bit, you would solve this main question that we have. Just distinguishing between expanders and non-expanders. So any improvement, even making this a lower power of log would give a.
So any such small improvement also will have some much computational complexity impact, to make a lot of hard problem easy or something like that?
Not formally, but I'll say right. So I guess that brings me to the next slide. The other reason why this is.
Okay, sorry, can you go back to the, what is the oh, any okay, sorry.
So the other, the reason this problem is interesting on its own, but it's also interesting because of the following reason. So there's this very interesting conjecture called the unique games conjecture, which gives a lot of optimal hardness results. And in particular, there are reductions from this problem, unique games, to all these problems. And the small set expansion problem is a problem easier than unique games that we still don't know how to solve. So essentially, small set expansion problem reduces to unique games, and it also gives hardness for all these. So I guess one way to say this is to say that the small set expansion problem is a bottleneck in existing algorithmic techniques for all these problems, because any improvement on any of these will solve the small set expansion problem. So
wait. So SSE will not. This is unique game conjecture.
Actually, you should say unique games problem. Yeah.
But you can also ask SSE conjecture that SSE is difficult.
Yes. Yeah. That would imply a hardness for all this. Yes. Yeah. But from an algorithmist point of view, if you want to improve any of these approximation ratios, we would end up solving small set expansion problem on the way. So we could as well look at that. Okay. So that motivates the small set expansion problem. So I'll set up some notation with regard to graph spectrum. So A will be the normalized adjacency matrix of our graph, and L sub G will be its Laplacian. And we'll be looking at the eigenvalues of the Laplacian. So there will be numbers from 0 to 2, and lambda 1 will be 0. Lambda 2 is larger, and so on, and up to lambda n. Okay, and I'll use the term top eigenvectors during the talk. What I mean is eigenvectors with small eigenvalues. So it's sort of inverted. Yeah. Okay, and I already mentioned what I mean by a small set expander. Okay, so let's see what non-expanding sets clearly have a direct correspondence to the spectrum of the graph, right? Because suppose you are given a set which doesn't expand in a graph, then you can look at the indicator function of that set, and suppose the set has volume delta, the indicator function has 2 norm length delta, and Laplacian exactly measures the number of edges leaving. Therefore, if the expansion is smaller than, let's say, 0.001, that means that if f is the indicator function, then f Laplacian f is smaller than 0.001 of the 2 norm. Essentially, this should say that we have a quadratic form on the left, and when you apply the quadratic form on this vector, it's giving us something really tiny compared to the 2 norm. So which means that this function f should really lie in the space of small eigenvalues of that quadratic form, which correspond to the top eigenspace. So f is close to the span of eigenvectors of small eigenvalue. So in conclusion, I mean, this is a very simple conclusion. It's just that I just want to say that indicator function of any non-expanding set is close to the span of the top eigenvectors. So this is a very simple observation. Okay, so there's a very silly subspace search algorithm that you can do. You can just look at the top eigenvectors, all of them, pick some epsilon net for those eigenvectors, and sort of you just want to do a brute force search on the top eigenspace. You know that if every non-expanding set is close to the top eigenspace, so if you do a brute force search, you'll output not just small non-expanding sets, you'll output every non-expanding set in the graph, and you can pick out the small non-expanding set. Okay, so you just pick an epsilon net for the unit ball in the top eigenspace, and you just go over every vector in the epsilon net, and you do you know that your set, the indicator function of the set, is close to one of these, and you just round it to a 0, 1 vector. Okay, so that's so. Stop me if I'm being vague. Oh, v sub I. V is a vector in the space, and you just want to round it. So we know that the indicator function of the set that we're looking for is close to the top eigenspace, but it's not really in the top eigenspace. So we go over every point in the top eigenspace, and we try to find an indicator function close to that vector. So v is a vector in the thing, and we're trying to find the indicator function close to that. So we just sort of do a brute force rounding. We say if a coordinate is more than half, round it to 1. If it's less than half, round it to 0. And this itself works. Okay, so the running time of this is clearly, it's a brute force search over some vector space. So it's going to take n to the power the dimension of the space, at least. Depends on the size of the epsilon net, but it's really just that. Dependencies like that. So, already we get a conclusion that, we can solve this small set expansion problem on graphs where the dimension of the top eigenspace is small. Right? You can just solve it by brute force. Okay. Okay. So this is a good branching point. So now. The only graphs that we have to worry about are graphs where there are a lot of eigenvectors for the Laplacian with small eigenvalue, like eigenvalue less than epsilon. Okay, these are the only graphs that we need to worry about if we are worrying about this problem. Okay. So here I'll present the talk will be split into 2 parts. First I'll talk about higher order Cheeger inequalities, and then I'll talk about construction of graphs with many eigenvalues. Okay. So what about higher order Cheeger inequalities? So again, we have the eigenvalues. So the Cheeger's inequality, the easy direction, says that for every subset, the expansion of the set is at least the second eigenvalue by 2. And you can easily derive a corresponding one for the first k eigenvalues. Suppose I know suppose I look at the first k distinct eigenvalues, lambda k is the kth eigenvalue. Then for every k disjoint sets, one of the set has expansion at least lambda k over 2. So I think I have a picture. So you take the graph. For every choice of k disjoint sets, at least one of them has expansion lambda k over 2. This is the easy direction of this, and it's very easy again. It follows from just looking at the Laplacian as a relaxation.
So that cannot be for any set of certain size, lambda k would be less than.
Yes, so at this point I have forgotten about the size. As of now, this is not about the size, it's just, we're just trying to find some sets.
Is there a version of this?
Here it does, for this it's true for every size. For every.
No, but like, is there a similar thing that says lambda k is less than expansion of sets of size at least something?
Yeah, it's sort of, because if you find k sets, you automatically, one of the sets is small.
Right, but I mean, how does it translate?
We'll see that. Yeah. Okay, so the difficult direction is, in Cheeger we say that there exists a set in every graph whose expansion is at most square root 2 of the lambda 2, and the higher order Cheeger version of that, one of the higher order Cheeger versions of that, is there exists order k disjoint sets, omega k disjoint sets, let's say k over 2 disjoint sets, whose such that the worst expansion of those k sets is at most square root of lambda k log k. Okay. So, and this was also derived by independently by Lee, Oves, Garan, and Trevisan, and Luca will be speaking about it. Maybe speaking about it in the next talk. And they also obtain another result where they obtain exactly k sets with whose expansion is k square times square root lambda k. So just to give a picture, so you have a graph, and what this is saying is you can always find omega k disjoint sets such that the expansion of each one of them is at most square root of lambda k log k. Okay, that is the claim.
How does the second claim make sense? I mean, it's much weaker, isn't it?
They're finding exactly k sets. Here we are finding k over 2 sets. So
place k by 2k.
no, but so this uses a bound lambda k here, and
If the lambdas all of a sudden jump, you don't know.
yes. Okay, so that was. So, a few comments about the higher order Cheeger. Firstly, the log k is necessary. One way to see it is through the noisy hypercube, or you could take an infinite graph on the Gaussian space also, and it will show that log k is necessary here. And you could possibly get exactly k sets and still get the same log k bound. It's conceivable. We don't know any counterexample. And this can be done efficiently. The whole process can be done efficiently. So what's the connection to small set expansion? It's a sort of the obvious connection I'm making here. It's just that if you find k sets, one of the sets has to be size at most 1 over k. So in some sense, it's saying that if there are k eigenvalues less than epsilon, then you will use this algorithm, or you will use this bound to find k sets. One of the set will be of size at most 1 over k, and its expansion will be at most square root of epsilon log k, or square root of the. So in some sense, you can hope to just use this along with the brute force search we had in the beginning to already get an algorithm for small set expansion. So this is an algorithm for small set expansion. If you have too few eigenvalues, just do brute force search. If you have too many, you can actually just find it using this. But it already implies that the SSE problem is easy unless delta is really small. For a fixed epsilon, delta has to be sufficiently small for the problem to be hard. And it also nicely complements with this this result in that, again here, this log k is sort of natural. If you improved this, if there was any better bound here, you would get an algorithm for small set expansion, the whole thing. So, so this log k is the correct answer here. Okay. Yeah. Yes.
Is also a formulation that makes sense of manifolds in continuous setting?
I'm not an expert. I don't know. Yeah.
Maybe Laurent will talk.
Yeah, we.
Okay. Yeah.
So those graphs that show that you can't get rid of the log k, do you know how to solve the problem today?
Yes, we know how to.
You said the blocks.
We know how to do it using the Lasser SDP hierarchy. So we don't. Yeah. Okay, so here I just want to give a hint of like a general overview of the proof. So because there's a nice algorithm underlying there, I'll probably skip some details. So how does the Cheeger's inequality proven? You take the second eigenvector or any eigenvector with any vector with a small Rayleigh coefficient. So any eigenvector gives you an embedding of the graph onto the real line because it associates a value with every vertex, a real value. And then you take this embedding and you sort of try to cut the embedding instead of cutting the graph. So you sort of try all the different level sets, and one of them will give you a cut whose expansion is at most square root 2 lambda. Okay, so that is Cheeger's inequalities proof. So how does the higher order Cheeger work? So here, we want to use the first k eigenvalues. So we have k eigenvectors. So I've written them down this way. So x1, x2, xk are the first k eigenvectors. All of them have a small Rayleigh coefficient. All of them are orthogonal to the ones vector. It's not necessary. Okay. So now, how do we use these k eigenvectors to find these k sets? So, as usual, the first k eigenvectors give us an embedding into k-dimensional space. Just like a single eigenvector gave us an embedding into one-dimensional space, the first k gives us an embedding of the graph into k-dimensional space. So the algorithm in k-dimensional space is very simple. The algorithm is you pick k random directions. So you pick k random Gaussian vectors. Each coordinate of these vectors are Gaussian. So, or just think of them as a k random Gaussian vectors, a k random axis in this space. And for each vertex, you project it along these k axes. And so you project this vertex on all the k axes and move the vertex to the axis it is closest to, or the axis to which it has the highest projection. So just set, essentially, you look at the k-dimensional, all the k projections that you have. For every vertex, you get k projections. You just map the vertex to the largest of that, and 0 everywhere.
Largest, like absolute value?
I think it doesn't matter, but let's say largest. Yeah. So you do this. So for each point, in essence, you're moving it to the axis to which it is closest. So now every point gets mapped to one of these k axes, and then you run Cheeger along each of these k axes. So in one axis, you'll find one set. On other axis, you'll find another set. So you'll find sets along every axis. But the problem is all of them won't be good. Some of them will be. We'll show that each axis gives you a good set, meaning a set with small expansion with constant probability. So if there are k axes, you'll get constant fraction of them will give you good non-expanding sets.
So I think there is an issue between k and k plus 1, right? For 2, you have one direction.
Yes.
And for 3, you have two directions. So somehow you are missing one because of the trivial eigen direction. So somehow you want to do it.
He's only going to get the constant times k anyhow.
Yeah.
Well,
doesn't care.
yes, but here he said, these k vectors.
So in some sense, for 2, what happens is you're actually finding 2 sets because the complement is also a set with small expansion. So I guess that I'm cheating there in some sense. In that way, I'm cheating, but it's.
Yeah, but for 2, you embed it in the real line, right? So there's just one dimension.
I guess you would think of it as 2-dimensional embedding with the other coordinate being constant, and it still run the algorithm. It will find. I think you'll end up finding 2 sets. One is a complement of the other. Because when you have only 2 axes, every vertex either falls here or to its complement. So in some sense, it gives us the
One axis gives the set, the other one gives its complement.
gives its complementing. Yeah. Right. I'm not very. I have to think about it.
I mean, you don't really use
Maybe
the
I'm.
first eigenvector
Uh,
and zero eigenvalue.
Yeah. Yeah.
So by 1 you mean 2 actually, and by k you mean 3. So I mean by,
No. Yeah.
you never use the all ones vector for anything.
Right. Yeah. Right.
I think that's the confusion.
Right.
I mean,
Just
it
get
works
it
though.
over.
It works.
It
the
works,
two-dimensional embedding, because all these things are clustering a two-dimensional embedding, right?
Yes.
So even if with the trivial constant coordinate, you still cluster the two-dimensional embedding.
Yeah. I think it works.
It actually works.
Yeah. I think the result that I stated is correct, even with. I mean, there's no offset by 1 there. It is. I stated the result correctly. Maybe I'm unable to make out what. Okay. So now. Okay, so I'll describe, so this is the algorithm. I hope the algorithm is clear. Now I'll describe the analysis, the main ideas of the analysis. So so we start with the k-dimensional embedding, right? The first thing we did was we projected along k random Gaussian directions. And we got a new embedding. Alternately, you could think of the projection along k random directions to just be a random rotation. So it's like it's just a random rotation of the old embedding, okay? And so now we have this new embedding, and then we look at each coordinate, each column, and then we just keep the largest and zero out everybody else. So each column here, we just keep the maximum value there. We are zeroing out everyone else. That's the new vector here. That's the new k-dimensional embedding. Now every vector is on an axis, one of the k-axis. And then we are running Cheeger on the rows. Every vector is in each column corresponds to a vertex in the graph, and we are just running Cheeger on the rows of this. There are k rows, and we're getting k different sets. So the only thing we need to prove is that the rows of this matrix have a small Rayleigh coefficient, because the scan rounding on a line, it works as long as your vector has a small Rayleigh coefficient, right? So that's the only thing we need to prove. And so let's see what are the main ideas step by step. So first thing we did was we projected along k random directions. So as I said, it's just a random rotation. So it doesn't affect any distances. So, and the Laplacian is, the numerator is a set of distances, the denominator is a set of distances. So the Gaussian projection preserves square distances in expectation. So the Rayleigh coefficient of these vectors is roughly the same, or with good probability, it's the same. Okay, not of every row, but on average, if you take any single projection, it's both its numerator in the Laplacian and the denominator, their values are the same in expectation. So just by Markov, it will get what you want. Okay, so this part is easy. Now it's the second part which is somewhat non-trivial, because what we did was we took the random rotation, we zero out all but the largest coordinate in every vector, every column. So in some sense, if you look at any column, it is losing all but one of its coordinates. So you are going to lose a large fraction of the L2 mass. So the length of all the vectors will decrease, right? But in particular, you expect to decrease by a fraction 1 over k, because you kept only one of the k coordinates. But you're keeping the maximum of the k coordinates. And if you think of them as independent Gaussian, the maximum of k independent Gaussians is square root log k. So you will get your length will decrease by a factor log k over k. 1 over k because you select one of the k coordinates, log k because you select the maximum of those k coordinates. And I guess the most interesting part of the calculation, or the most interesting part of the calculation, happens in computing the numerator. So essentially what we did, so far everything was smooth, right? We did a random rotation that was smooth. The zeroing out operation is not smooth, and that is bad when you're looking at the numerator. Numerator is looking at the difference between values, edge lengths, xi minus xj square. So if the two things are not smooth, then it's a problem. So that's where anything interesting happens at all, right? And over there, this sort of rounding, where you take k random projections and you move it to the largest projection, has been used earlier in several algorithms based on SDP rounding, and we could sort of appeal to that. Essentially, we have to appeal to a lemma which looks like this. So if I take k random Gaussians, x1 through xk and y1 through yk, such that xi and yi are 1 minus epsilon correlated. So xi and yi are close to each other, but xi and xj are independent. So you take x1, y1, 1 minus epsilon correlated, x2, y2, 1 minus epsilon correlated, and so on, k such Gaussians. And then you look at the maximum, which coordinate is the maximum in x and which coordinate is the maximum in y. The probability that x and y have different coordinates as maximum is at most square root of epsilon log k. And this is the, okay, so more geometrically, the way I think of it is, you take the Gaussian space, you connect points which are epsilon correlated. Essentially, I'm being very rough here. So let's take the sphere in very high dimensions and connect points which are epsilon away. On the sphere in very high dimensions, connect points epsilon away. Now look at sets of size 1 over k. The expansion is square root of epsilon log k, and that's where this number is coming from. And
only look at caps.
At least, so you take any set of size 1 over k of a unit ball in very high dimensions, and your edges are epsilon length edges there. The expansion of such sets is square root of epsilon log k, and that is the limit up to which we can.
So I can't parse this statement. You're saying that probability that for that there exists some I in which.
So here argmax is, it's picking out the index which is largest.
What's argmax sub I?
Should be,
Index.
it's just the index which is the largest.
But the geometric thing is better. So you connect any two points on the sphere which are at distance at most epsilon away, and now you partition the sphere into k parts.
Or even just any single set. Pick any set of size 1 over.
Measure at least 1 over k.
Yeah.
Relative to this graph, it expands at least this. That's the step.
This is the expansion.
Is the constant below capital epsilon?
Sorry?
Here, in capital O, there is constant. It's epsilon.
Yes, so there's a absolute constant. I think it's not, I'm not sure if it's an absolute constant, maybe there are lower order terms. But it's exactly that number, the number which is the expansion of sets of size 1 over k in the Gaussian space. And this is just an estimate for that number. Otherwise you could write a double integral which corresponds to the expansion of the cap on the sphere. And that will be the number. This is an estimate. I think this is a pretty good estimate.
The probability is over choosing a random I. You expect the.
Oh, this is just okay. So this setup is just, you're picking xi, yi, 1 minus epsilon correlated Gaussians independently, k times, and now you look at the x1 through xk, look at the index in which the maximum happens, and look at the index for y1 through yk, index maximum happens, if they are different.
Yes.
And the probability is just over the choice of the Gaussians, over the Gaussians that you picked. So if you just, this is just an experiment in like Gaussian, if you just.
Isn't it that the least expanding sets are just spherical caps?
Yes, yeah.
These have, you should calculate, but these have such an explanation.
Yeah. Okay. So, So there's one important detail which has missed out. In this whole algorithm, we need to use the fact that you actually have k different eigenvectors. If you had k minus 5, you can't get k sets. You can't hope to get k sets. So far, I haven't used that fact at all. All these facts are true even if you didn't have k different eigenvectors. You just had an embedding in k dimensions, which actually was k over 2 dimensional. Okay. So where that shows up is really you also have to. You're trying to control a ratio of two quantities. You want to control the denominator. So which means you have to control the variance of the denominator. And in order to control the variance of the denominator, that's where we will use the fact that the original eigenvectors that we used were orthogonal to each other. So which means it was a genuinely k-dimensional embedding. Okay, and so if you have a k-dimensional, if you have n points in isotropic position in k-dimensional space, the average inner product between any pair is at most 1 over k. So essentially, if you take k-dimensional space and if your points are in isotropic position, that means that they are sort of spread out. They don't face each other. They're not all clustered in one direction. So the average inner product is low. The correlation is low. And that's how we are able to control the variance of this denominator. We need to control the variance of the denominator. And so I'm not showing the calculation, but it's, there's some you need to write it out in Hermite polynomials and so on, but it works out. It's not. Okay, so I have 10 minutes. So now I'll go to the second part of the talk, which is, so as I said, the small set expansion problem is non-trivial only when the graph has many, many large eigenvalues. Okay. So let's give it a name. So let's threshold rank of epsilon of G be the number of eigenvalues of the graph that are less than epsilon of this of the Laplacian. Okay? And we know that the subspace runs in into the threshold rank. So now the question is, our real problem that we are trying to solve is we are trying to find either a non-expanding small set, or we are trying to conclude that G is a small set expander. Now, if G is a small set expander, how many eigenvalues can it have? Right? Intuitively, each eigenvalue is giving you a sparse cut. So if you have too many of them, maybe one of the sets will be small, and it won't be a small set expander. So that's the question. So how many eigenvalues can a small set expander have at all? And Aurora Barak-Steurer showed that a small set expander cannot have more than roughly n to the epsilon eigenvalues, like a polynomial number, n to the epsilon. Okay? Eigenvalues. So in particular, this gives a sub-exponential time algorithm for this problem. This is the main core of a sub-exponential time algorithm for the problem, is to just say either you have less than n to the epsilon eigenvalues, then you can do brute force search. If you have, and you cannot have more than n to the epsilon, n to the root epsilon, but you cannot have more than n to the root. So that's why you're done.
So is this tight? Is this achievable?
Yes, so that's the question. Is this tight? And now we have a construction of this thing called the short code graph, which I'll describe now, which has 2 to the log beta. It's not polynomial, it's 2 to the poly log, where the poly is less than 1. Right? So now we know that you can have up to this many different large eigenvalues, 2 to the log beta to the n, and it's at most this much, but there's still a gap.
What is beta?
So beta is less than 1.
Less than 1.
Yes, it is less than 1 because we have it. And it depends on epsilon also. It's so in some sense it's very tiny. You can think of it as a tiny constant. It's a tiny constant. 2 to the
epsilon, like with n to the epsilon?
Not in the constant size sets of the hypercube don't have expansion. Like if I just take sets of size delta times 2 to the n, I can, like, the expansion is delta is constant. Delta times 2 to the n, then it's not.
Some constant fraction of the.
Yeah, if I take a constant fraction of the hypercube, I can construct sets which are not expanders at all.
Like a sphere.
Right, but it's
Yeah.
small set expanded for smaller.
Yes, so that, but right, yeah. But here, delta is a constant.
No, if your bound is correct, this will be an amazing improvement of the algorithm, yes? For
Yes,
If
that's
bound
right.
is correct.
If the bound is correct.
if it's sharp, if it's sharp.
The bound is sharp. Well, yeah. Or rather, if you could push this bound, then it would, almost surely say that small set expansion is not NP hard, right? If you could make this instead of n to the epsilon, if you made it 2 to the root log n or something.
So the small set expansion problem is either uninteresting or easy when delta is less than constant, or?
It's probably harder, but the problem itself is harder, but we don't know how it relates to unique games. So that's why I'm concentrating.
So, I mean, look at unique games on the hypercube. The reason why you can solve it is because hypercube is a small set expander for delta less than constant, but it also has n to the epsilon.
Yes, but there's no, right, I agree, but we don't know of a formal connection. Yeah, I agree. But the formal connection holds only for constant delta. But, for constant delta, this itself is an interesting, so let's worry about constant delta. And so this construction led to some improved gadgets and into SDP gaps and so on. And in particular, Kane and Maker use this sort of construction to construct an n-point L2 square metric that requires 2 to the root log n distortion into L1. So,
So this is improving of Hot-Vishnoi.
Yes, and it's so this we'll see this graph looks like the Hot-Vishnoi in some sense, and all the parameters improve exponentially if you try to.
2 to square root.
It was root log n. Now it becomes 2 to the root log n. Root log n is probably the answer. Wait, don't know. Yeah.
What is the answer?
I don't know.
What is the expected answer?
Root log n maybe because we have
I see.
because
Yeah,
root log
yeah,
n
yeah.
algorithm.
Right.
Okay,
Amazing.
so I'll describe the graph at a very high level since I have only about 5 minutes. So the graph is okay. Let's start with the more traditional graph, which is the noisy hypercube. Okay, so here I'll describe a Frankel-Rodel type noisy hypercube. You take the hypercube, you connect points which are epsilon n away on the hypercube. So this is a graph, and its eigenfunctions are. So if you look at dictator cuts, they are very sparse cuts. They cut epsilon fraction of edges. Or f of x equal to x sub I is actually eigenvector with eigenvalue epsilon on this graph. Okay, so I'll skip the calculation. It's not that hard. And the eigenfunctions of the noisy hypercube are really polynomials. So because the noisy hypercube or the Frankel-Rodel graph is a Cayley graph, right? And if you take a Cayley graph, its eigenfunctions are just the characters, right? So now, so if you look at degree 1 polynomials, Fourier-Walsh degree 1 polynomials, their eigenvalue is epsilon, roughly epsilon actually. And degree 2, then their eigenvalue is roughly 2 epsilon. And if you look at degree D, then their eigenvalue is D times epsilon. Okay.
So the first Hot-Vishnoi, I don't know, you call this the shortcut, but how does the original Hot-Vishnoi integrate without, let's call it Hot-Vishnoi. Doesn't this also have like polylog, large eigenvalues,
Yes.
and small set expansions?
Yes, this is so. But polylog, we are getting 2 to the polylog, so that's the difference.
Oh.
So right, so we're coming there. So these are the eigenvalues, right? So basically the moral is the top eigenspector space of this graph are low degree polynomials. It's just because you look at the eigenvalues, they sort of increase as the degree increases. So the eigenvectors with low eigenvalue are the low degree polynomials. Okay, and why is this graph a small set expander? That is because of hypercontractivity. Okay. So you take any vector space. A vector space is hypercontractive if the 4 norm and 2 norm are comparable there within constant factors, let's say. So, and if a subspace is hypercontractive, that means it doesn't have sparse vectors in it, because for a sparse vector, the 4 norm is much larger than the 2 norm. Okay. And okay, essentially the point is, if I look at any graph, take any graph, look at the top eigenspace, look at the subspace spanned by the top eigenvectors. Okay, if that subspace is hypercontractive, then there are no small expanding sets because there are no sparse vectors in that subspace. Okay. So the reason why the hypercube has good expansion, small set expansion, is because of hypercontractivity, or rather, one proof of that is through via hypercontractivity. Okay, so so basically the the proof that the hypercube is small set expansion uses two facts. One is that the eigenfunctions are low degree polynomials. Secondly, that the low degree polynomials, if you look at low degree polynomials over the graph, over the hypercube, their 4 norm is comparable to the 2 norm. Okay. And that's the reason why you're getting small set expansion.
This is hinging.
Huh?
This is hinging.
This Bonham. Yeah. Okay. Okay. So now let me come to how we improve on the hypercube. So we have the simple Frankel-Rodel graph on the hypercube, right? And what it was a nice small set expander. It was a very nice small set expander, and it had n eigenvalues which are large. Just look at the dictator functions. They are small eigenvalues. Okay, so there are n sparse cuts, which are the dictator cuts, but the number of vertices is 2 to the n. Right. So although this has n sparse cuts, the number of vertices is 2 to the n. So then, in terms of the number of vertices in the graph, you're getting log of the thing. So the idea is, let's pick a subset of the vertices. Do we really need all the 2 to the n vertices? Let's pick a subset of the vertices, like a de-randomization in some sense. We pick a subset of the vertices and hope that the dictator cuts are still sparse cuts. And the second point is important, that the subgraph that you get is still a small set expander. The proof of small set expansion should still hold, and the dictator cut should still be sparse cuts. So you want to pick a tiny subset. Ideally, you would just want to pick, let's say, polynomially many. Let's say if I pick just n to the 100 points and had this property to be true, that would be great. And and so that's exactly what we do. We pick a subset of the hypercube, we pick some subset and look at the induced Frankel-Rodel graph, and we translate the proof of small set expansion onto this subgraph, and the proof of and the eigenvalues onto this subgraph, and that's how we get the improvement.
Is it important that the set you choose, you have a constructive way of describing it? Or, I mean, would a random set work?
Okay, so right. So firstly, a random set would not work because there won't be any edges in a random set. So this is a very sparse. Frankel-Rodel graphs are very sparse. So and secondly, as it turns out, carrying out the proof that the graph is small set expander on the subgraph is actually fairly. Okay, I won't describe the graph construction itself. I'll just say, there are two parts to the proof that there is small set expander. So to say that, firstly, you want hypercontractivity to still hold for low degree polynomials. This is easy because you could just pick a subset which is a k-wise independent subset. Then you can actually preserve the expectation of all low degree polynomials. That if I just pick a k-wise independent subset, I'll preserve the expectation of all low degree polynomials, and which means the whole space is the same as a subset. And note that the 4 norm is just of a polynomial is just expectation of p to the 4, right? So if the expectation is the same, then I preserve the relation between the 4 and the 2 norm. So that's so that part is easy. So you can pick any subset which is sort of k-wise independent. That will preserve hypercontractivity. Okay. The other part, which is the non-trivial part, is that originally we had this fact that the top eigenspace of the noisy hypercube are low degree polynomials. Now when you pick a subgraph, when you just pick a subset, you could have other functions which are also have a small eigenvalue, like some high degree functions which have a small eigenvalue. So we want that only the top eigenfunctions, the only top eigenfunctions on the graph are low degree polynomials. And it turns out, it's a Cayley graph, it's still a Cayley graph, so you can write down exactly what the eigenvalue has to be. And if you try to prove this fact, you end up, you need a very special sort of structure on the subset. In particular, as it turns out, for us, for our construction, somebody had already proved it, so we could use it. It was a non-trivial. It would have taken us another 6 months to prove it, or maybe never, if we had to do it ourselves. So it's a non-trivial result. Essentially, this saying that the top eigenspace consists of low degree polynomials corresponds to a local testing result for the subset that you're picking. You're picking a subset, so you're probably thinking of it as a linear code. Right? You're picking a linear code, and then so bounding the eigenvalues corresponds to local testing of that code. Yeah, I think I'm already over time. So essentially there were 2 ingredients. One was local testing of the subset, and the other is k-wise independence. These 2 meant that we could translate results from the hypercube to the subset. And actually you can translate more results. You can also translate majority stablest and some version of KKL into that subset. Okay, so I'll spend maybe 1 or 2 minutes on open questions. The first open question is, this is still open. We got some bound here and some bound here. There is still a gap. This is a very simple spectral graph theory question. You can forget about all that I said so far. You just ask this question: if G is a delta small set expander, how many eigenvalues, very small eigenvalues, can it have?
So improving the Hot-Vishnoi all the way to square root log n, this will correspond in this picture to the square root log. This will correspond in this picture to improving your result,
yes,
from the n to the epsilon.
Yes, if we improve the lower bound,
so
it
this
could
will still be. Oh, okay.
Yeah. So even if you improve the lower bound to this, it could possibly lead to square root log n lower bounds for the sparsest cut, and it could lead to new gadgets, which could be already there are a few applications of short code in hardness proofs.
But this will still support the conjecture that unique game is difficult.
Yes. Yeah. Okay. So another question which sort of realized recently is just how do you identify or certify vertex expansions? So you're given a graph. Okay, you want to distinguish whether there is a set whose vertex expansion is less than epsilon, or every set has vertex expansion at least 0.1. Or in one case it's not a vertex expander, in another case it is vertex expander. So here I am not putting any restriction on the set size. Okay, I'm not putting any restriction on the set size. It's just a question of, given a graph, find out if it's a vertex expander. It turns out that this problem we don't know how to do it, and it's harder than small set expansion. So small set expansion reduces to this, and this problem is interesting on its own. Just certifying that a graph is a vertex expander, where when I say vertex expander, I mean some constant like 0.1. Right?
Maybe you want the quantifiers the other way, so you want to find an algorithm such that given a graph G, do this thing.
Yes. Well, yes. And I'll stop here. Thanks.
So one is this k-wise that you talk about. K is some linear in D? Or
Constants. Again, linear in D, but in the actual application, you want a constant. You're using a constant twice independence because you're just trying to fool degree 100 polynomials or something. Degree D polynomial. D is a constant.
And then there is this 1 minus epsilon versus epsilon in your paper, like the story and so on. So this, you talk about the rank epsilon most of the time, but then in the result.
In some sense, I used constant expansion instead of saying almost perfect expansion. But these things are equivalent. You could work with a tiny expansion.
So the random subset does very well as far as k-wise independence, but it does terribly as far as local decodability.
Yes.
But really, the local decodability, is it kind of a necessary thing, or it's just a technical?
I think it's hard. At least for this route, it is sort of necessary. And there are more, like for random subset, the reason it wouldn't work is when you pick a random subset, with high probability you will not see any edges of the hypercube. Like it will be an independent set. The induced subgraph will be an independent set. And that's sort of the difficulty in constructing these
but that's
instances.
kind of this, similar to local decodability, because an edge would mean that you find some relation, no, between.
Yes.
So it's related.
It's related, but yeah, yes, it is related.
So is small set expansion equivalent to checking hypercontractivity of an appropriate subspace for the low eigenspace?
Yes, but you have to pick the parameters correctly. You have to pick for right choice of parameters, it is equivalent.
You mean there's a reduction?
There's a reduction, yes. Yeah.
Is there some thing that some codes that if they will be found will improve the results, or can you identify what type of thing you?
Yeah. So the sort of codes that we're looking for is think of Hamming code, right? Hamming code has distance 3 or something. So you think of a code, actually 3 bits, right? So we're looking for a code of distance 100, let's say, whose distance is 100, but it's locally testable with 10% queries, meaning so because it's distance 100, you expect 2 to the n over n to the 100 code words, right? You expect to pack basically balls everywhere in the thing, but you want it to be locally testable, meaning after reading 10% of the coordinates, I should be able to distinguish whether close or far from that. So it's really that regime.
Let's end once more.